We often think of exponentiation as a rapidly growing function or a rapidly shrinking one depending on the argument. This is just exponentiating real numbers, but of course, you might have heard of exponentiating complex numbers. However, it is possible to define exponentiation of many other things, including vectors, ddx or any other differential operators, as well as an entire vector field. Just to be clear, these are not hallucinated by mathematicians, they have concrete applications in other areas of maths. These exponentiations, as I will explain later, are really different at first glance, so why do we use the concept of exponentiation to lump them together? To answer the why and really understand these weird exponentials, we first need to revisit what exponentiation really is. If you ask different people what exponentiation is, you will get at least 3 different kinds of answer. A function whose derivative equals itself with the extra condition that exponentiating 0 gives 1. Or that it has a series expansion as shown here, or, very often as a first introduction as interest rates, the limit of a certain expression. For this video, I'm mainly going to use the derivative property of the exponentials, but we modify this definition a little bit. We instead consider another function g of t that satisfies another set of related conditions. Don't worry, g of t would actually just be exponential of tx, and the conditions here are just what we expect exponential of tx should satisfy. Then e to the x is simply plugging in t equals 1. Now this is quite a neat way of thinking about exponentiation because rather than thinking of e to the x as a single point, g of t forces us to think of e to the x as the endpoint of a journey. More specifically, this journey starts from g of 0, which according to our conditions would be 1. And we work our way towards the endpoint, which is going to be e to the x or g of 1. So exponentiation can be thought of a little more dynamically. It is actually a journey, a process. Of course, this journey, g of t, is not just a random journey, it still needs to satisfy this condition of g of t. This condition tells us that initially, the velocity is x because the conditions imply that g prime of 0 is x. Then, at any intermediate point g of t during this journey, the velocity is x times g of t. To find the exponential of x, we stop when we reach 1 unit of time to get g of 1. Now, something that will be useful later on is to notice the setup at the start and the intermediate points along the journey. The initial setup includes the starting point, which we choose to be 1, and the initial velocity x, which is something that we try to exponentiate. To go from the initial setup to the general setup in the middle of the journey, we simply multiply the whole initial setup by the current position g of t. The exponentiation of x is then the endpoint of the journey after 1 unit of time has passed. Thinking of exponentiation this way might not be new to you, but this framework helps us understand how to exponentiate more exotic objects like vectors, derivatives, and vector fields. Let's start with how typically mathematicians exponentiate vectors. In the context of manifolds, which I have briefly introduced in the previous video, mathematicians have defined the exponential map for vectors. To define the exponential map, the vector needs to be a tangent vector on the manifold, and the result would be another point on the manifold. But why do we choose this point? Here, I'm using the 2-dimensional surface as an illustration, but actually it could be generalized to higher dimensions. First, think of this vector v as an initial velocity vector, and you are initially traveling from the point P. after traveling for even just a moment, we can no longer travel at the same exact original velocity because this initial velocity vector is not tangent to the surface anymore. We still want to kind of travel at this velocity, so we make a slight adjustment. Simply rotate the vector so that it is now tangent to the surface again. A little more technically, this rotation is such that the rotated vector coincides with the projection, or the plane containing the unrotated and rotated vectors is perpendicular to the tangent plane. But in any case, the spirit is to make minimal adjustment to the initial velocity vector to make it tangent again. So this rotated vector is our velocity from this point, say Q, onwards. But of course, we face the same problem when we proceed. This already rotated vector cannot be the velocity even just a moment after, and we need to do the same little rotation to make it tangent again. So we actually need to continuously slightly rotate this initial velocity vector along the way. This process of continuously rotating a tangent vector along the way is called parallel transport. But for the sake of exponentiation, when should we stop this parallel transport process? Recall that we are trying to exponentiate this vector v, which has been described as the initial velocity. We let this go on for exactly 1 unit of time. Wherever we end up would be defined as the exponential of v. The notation here has a subscript p under exponentiation to indicate that the whole process starts at the point p. But what is exponential about this process? Compare this with the exponentiation of normal numbers, where the initial setup indicates a particular starting point and initial velocity, and the intermediate setup is obtained by simply multiplying the entire initial setup by the current position. The exponential is the endpoint of the journey when 1 unit of time has passed. For exponentiation of vectors, this starting point is now changed to p, a specified point on the manifold. The initial velocity now is really a velocity vector v. This is also the thing that we try to exponentiate. To go from the initial setup to the intermediate setup, this time we parallel transport instead of doing any multiplication, so that this is the intermediate setup. Very similar to the case of normal numbers, we stop the process after 1 unit of time. The end result is the exponential of the initial velocity. Now, some of you might be thinking there is something wrong if this is meant to be generalizing exponential of normal numbers. Let me explain. If we consider a specific case where the manifold is just a plane, or even simpler, just a number line, then throughout the process of exponentiation, in particular the parallel transport process, would just be a normal translation. This is because there is absolutely no obstruction to traveling with this velocity on a flat surface, so we don't need to rotate to keep it tangent. So with the parallel transport just being a translation, the velocity in the intermediate setup is still v in this case, same as the initial velocity. But this is at odds with the exponential of normal numbers because the initial velocity and the intermediate velocities are, in general, different. Now, there are 3 different levels of resolutions to this problem. The easiest level is to simply say that they are completely separate things, they are only spiritually similar. One is not necessarily a generalization of the other. The second level is to recognize that on the complex plane, we can restrict ourselves to only thinking about the unit circle centered at the origin, and always start at the point 1 as you do for exponentiation of normal numbers. A tangent vector at 1 can be identified with a purely imaginary number, say I theta. This is because in general, for any complex number, we can identify it with a vector emanating from the origin towards that complex number. So in the case of an upward vector, it corresponds to a purely imaginary number I theta. So with a tangent vector being described as I theta, if we exponentiate the vector during the parallel transport along the circle, we will get a point which actually is e to the I theta in the complex number sense. So at least in this case, they are not just spiritually connected, they are literally the same in this case. The third level is that they are actually connected. Exponentiation of vectors in terms of parallel transport really is a generalization of the normal number case. But to really understand the connection at this level, we need more advanced concepts in differential geometry, which is a story for another time. For now, just know that to exponentiate the vector v from the point P, we simply parallel transport the whole setup and stop when 1 unit of time has passed. Okay, so this is how we can exponentiate vectors, but what about derivatives? The derivative itself is an operator, which means that it takes a function as input, in this case the squaring function as illustrated, and outputs another function, which is the doubling function as illustrated. The exponential of d dx that we are going to define is also an operator, but we will see how an input function f of x changes to the output function g of x under this exponential operator. This time, we go back to exponentiation of normal numbers and see how we can modify it to exponentiate derivatives as well. For the initial setup, what should be our starting point? It would make a lot of sense for it to be our input function, say f of x. The initial velocity is something that we exponentiate, so this should be a derivative. In this case, it should be a derivative acting on our input function. But hang on, what do you mean by a velocity being a function? Visually, we can think of a function as its graph. Here, I'm plotting the graph in a 3D space just on the vertical plane. This vertical plane can be thought of as the time t equals 0 slice, and we evolve this function f of x in time. This is the journey that we need to take for exponentiation. More explicitly, this time the journey g of t for a fixed t equals t naught, g of t naught is itself a function of x, which you can think of as a snapshot when the function is evolving. Because g of t naught is a function of x, it makes sense to think of it as g of t naught x, so that g is simultaneously a function of t and x. And along the journey, we simply increase the value of t. Okay, so the initial setup is now from g of 0x, being the input function f of x, and somehow the rate of evolution of this function is its derivative. What does it mean? If we fix the value of x and simply let it evolve like before, then this point will also make its own trajectory. When we say the rate of evolution is the derivative of f at the start, we mean that initially, the height of this point changes at a rate of f prime of x. Equivalently, the slope along the t direction is f prime of x initially. So this explains the initial setup, particularly what it means for the velocity to be a function itself. But what should the intermediate setup be? If we go back to the exponentiation of numbers, rather than thinking of multiplying the whole initial setup by some number, alternatively, we can think that the velocities are actually x times the current position. So in the case of exponentiating derivatives, the initial velocity is the derivative of the input function. It would be natural to take the intermediate velocity to also be the derivative of the current function. This is the spirit, but we need to be careful with our notations. First off, we have already been thinking of g as a function of both t and x, so we need to adjust the current function to be g of tx. The derivative is denoted using a partial derivative, which might not be familiar to you, but basically it means that if we fix t, this is a snapshot function of x, then take the derivative with respect to x. In fact, a shorthand for this intermediate setup is this equation involving partial derivatives. The left-hand side denotes exactly our notion of velocity in this context, because the velocity in this context also starts by fixing x and tracking its velocity when it evolves. So the velocity is really fixing x and taking derivative with respect to t. Finally, the result of exponentiation would be g of 1x after a unit of time has passed. But can we write down this exponential more explicitly? It seems like we need to solve this partial differential equation, which you can, but you don't need to. After all, this partial differential equation just means that the slope along the t direction, that is partial g partial t, is the same as the slope along the x direction. So if you compare going towards the x direction by a very tiny amount, say epsilon, versus going along the t direction by epsilon, since the slopes are the same, in these two situations you end up with roughly the same height. You can think of going along a sort of 45-degree angle, and at least for a short time, you are not going up or down. But of course, this is not just at this point. For any other point, we can still run through the same argument. And again, going along this 45-degree angle, we are going level. So in general, going from the time t slice to time t plus epsilon slice, we simply have to translate along this diagonal direction for a tiny bit. However, once we are on this new time slice, we can basically use the same argument because we still have this partial derivative condition. So during the whole time evolution, because of this partial derivative condition, we can actually think of it as a simple translation. Thinking about it this way could directly help us kind of solve the partial derivative equation. At a particular time slice, we can obtain the value of g of tx by simply tracing back where it comes from. At time t equals 0, the function is f of x, our input function. And the point when we trace back where g of tx was translated from would be exactly the point f of x plus t, because the 45-degree translation means that you have translated t units along the t direction and also t units to the left along the x direction. Because the whole thing about this translation is that it stays level, we have these two being the same, i.e. g of tx is equal to f of x plus t. If we go back to the exponentiation, which is what this whole thing is for, ultimately we want g of 1x, which according to this result we have just derived, means that the final destination is f of x plus 1. So what exponential of d dx does to a function f of x is to shift the argument in the function by 1. In fact, more generally, because we have this relation g of tx equals f of x plus t, and g of tx is supposed to be exponential of t d dx acting on f of x, we have this more general statement about exponentiating derivatives. This operator is typically called the shift operator because it simply shifts the argument of the function by t. But this shift operator can be more general, especially for multivariable functions. For functions with two variables, the shift operator would be composed of partial derivatives, and the partial derivative with respect to x would shift the x argument, and the one with respect to y would shift the y argument. This can be further generalized to higher dimensions with more variables and partial derivatives, but it's usually succinctly written like this. This more succinct equation is often seen in quantum mechanics, and in the context of quantum mechanics, this exponential of derivatives is called the translation operator. However, the exponential can act on something other than d dx and linear combinations of it. The whole discussion hinges on the intermediate setup being a partial differential equation. The reason why the velocity of this journey through functions is partial g partial x is because we are exponentiating d dx. If we want to exponentiate, say, the second derivative, then this equation would have changed to the velocity being the second partial derivative with respect to x. Of course, in that case, the initial velocity would have also changed. The intermediate setup, as we discussed, has changed, and at the end of the journey, we would have the exponential of the second derivative. But this time it will not be f of x plus 1, it would be whatever g of 1x is, when g satisfies this differential equation and g of 0x is our input function f of x. More algebraically, in this exponentiation of the second derivative, we are finding g of 1x where this g satisfies a differential equation and an initial condition. This was our previous endpoint of the journey. The equation is what we have been calling the intermediate setup, and the initial condition is the starting point of the journey. Of course, it is not limited to the first or second derivative. Any differential operator h hat can be exponentiated in a similar way. Just replace the right-hand side of the differential equation by h hat acting on g. In fact, more generally, if we are not just thinking of the endpoint, then the intermediate function's g of tx is represented by the exponential of th hat acting on f. Now, throughout this chapter, we focused on the case when the operator is d dx, and this differential equation has a simple solution. G of tx equals f of x plus t. However, for general operator h hat, there might not be such a simple solution. In this case, the exponential of th hat acting on f of x works as a formal solution, so that you don't always need to write down the full set of equations and initial conditions just to refer to this function g of tx. Just a word of warning though, this h hat should be independent of t. Of course, as a differential equation, it could depend on t, but the formal solution here wouldn't work if h hat depends on t. If instead, the equation has the operator depending on time, then the formal solution would have been way more complicated, and it is not exactly an exponential anymore, but something called a time-ordered exponential. But in any case, now we know what the exponential of derivatives mean. It is just a solution to the differential equation subject to the initial condition given by the input function f. A vector field is obtained by attaching each point in space with a vector. I'm just showing some vectors here to avoid clutter, but in theory there is a vector attached to every point. This can also be exponentiated. The result would be a function that takes a point p in space to another point q, which would be the exponential of the vector field acting on p. How does the exponential work? Well, we just go back to the exponential of normal numbers and see how we can tweak it to exponentiate vector fields. For the initial setup, we can choose the starting point to be the point P in space, and the initial velocity to be the vector attached to that point. So visually, we start off at a point in space P and just see what vector is attached to it. This will be our initial velocity. Now, in the intermediate setup, we should have the velocity to be the vector attached to the current position g of t. This is because in the normal numbers case, the velocities in the initial and intermediate setups have a very similar relationship with the current position. In this number case, the relationship is that the velocity is multiplying the current position by x. So, in the vector field's case, both setups should be similar, which would be that both velocities are vectors attached to the current position. And again, the endpoint of this journey, after 1 unit of time has passed, would be the exponential of the vector field acting on p. The whole setup is basically asking us to treat the vector field as velocities at the different points. So visually, we start at the point P. Then we follow the vectors in the vector field and treat them as velocities. The trajectory here is the journey g of t. The destination, when 1 unit of time has passed, would be where the exponential of the vector field takes us from P. In general, the intermediate points are also described by the exponential of t times the vector field, where you can think of each vector in the vector field shrinks by a factor of t. The exponential of this family of vector fields is aptly called flow, because it really lets the point P flow to other places along this vector field. There is one kind of vector field in particular that will be useful later on in the video series, a linear vector field. This is a specific kind of vector field in which the vector attached to each point is related to its position. Pick a particular point, we can associate it with a vector emanating from the origin. Call this vector x. Then the vector attached to this point is ax for some matrix A. If every vector attached is constructed with the same matrix A, then this vector field is a linear vector field. Because the vector field is constructed with the matrix A, it would make sense to abbreviate this whole vector field to just the matrix A. So when we try to exponentiate this particular vector field, as usual, we consider how it flows. More precisely, given a random point with the associated vector emanating from the origin being v, the flow along this vector field is going to be described by an exponential. The resulting vector is going to be exponential of t times the vector field acting on v. However, in the case of a linear vector field, we can simply abbreviate this vector field as the matrix A. This is actually how we exponentiate matrices. This idea of exponentiating matrices viewed as vector flows has been presented on 3Blue1Brown's channel as well. In fact, equipped with this intuition of matrix exponentials, it is possible to intuitively understand this exponential relationship between determinant and trace. But of course, we need to understand the intuition of trace first. Again, that's a story for another time. So exponentiation of lots of exotic objects really stems from this journey framework. The exponential of vectors involves the idea of parallel transport to go from the initial setup to any intermediate setup. Exponentiating derivatives requires the intermediate setup to imitate the initial setup in the sense that both velocities are derivatives of the current function with respect to x. And for vector fields, the intermediate setup also imitates the initial setup so that both velocities are just vectors attached to the current position along the journey. And that's it. I'm sorry that I have been away on YouTube for a long time, so a really big thanks to the patrons who are still supporting me. As usual, like and subscribe if you enjoyed the video, and I will see you next time.